Welcome to this video. Thanks for taking the time to watch. Sorry the technology didn't work today in class, but here we are. So the pressure volume curve, this is the cardiac cycle. We start at A, goes to B. While A is going to B, we are undergoing filling the ventricles. This is also the compliance line. We're going to walk through all these, don't worry. B goes to C, C to D, D to A, and the cycle just continues. We're going to isolate points and segments. So we're going to have points over here. And segments over there. So point A, what can we say about point A? At point A, mitral valve is open and the aortic valve is closed. We are filling the ventricle right now, so the blood has to go from the atria to the ventricle. Mitral valve got to be open. B, at this point, mitral valve is closed. Aortic valve is also closed. We are also going to label point B as preload. And we'll find out more later why. C, at this point, mitral valve is still closed, but the aortic valve is now open. We are in systole, blood's leaving the heart. We are also going to associate point C as afterload. And you'll see when we start playing around with afterloads how this changes things. D, at this point, mitral valve is still closed, and now the aortic valve is now closed as well. We are also going to attribute point D to contractility. We have the Frank-Starling curve. The Frank-Starling curve rides on this line right here. So point D is our imaginary line. It always kind of sticks wherever that Frank-Starling curve is. So as you alter contractility, that point D is going to shift left and up or right and down, depending on what is going on with the contractility. Moving over to the segment side. We have segment AB. This is our compliance line. Remember compliance, increasing volume, but a very small change in pressure. So AB, compliance, diastole, filling. These are the words associated with that AB segment. We have BC segment. This is our isovolumic contraction. What are we doing here? We are generating pressure to overcome the opposing forces to flow, which is the aortic pressure, which is we use as systolic blood pressure, and it is our afterload. We have to overcome that pressure to get the door open, and that's why C is our afterload. C to D, this is systole, this is ejection. We're leaving the heart now. D to A is our isovolumic relaxation. Now the heart is relaxing, dropping its pressure, and that pressure has got to drop below atrial pressure so that the mitral valve will now open and filling will start, and the whole cycle will continue on and on and on. So as you're studying this, make sure you understand what the points do and the segments. So now what we're going to do is we're going to alter this pressure volume loop to show stroke volume. So at point B, we can also call point B is your end diastolic volume. This is the last little bit of volume of blood right before systole begins, when everything closes. Likewise, point D is our end systolic volume. So I'll put those here as well. So B, end diastolic volume, point D, and systolic volume. So if you just draw a line from edge to edge, that gives us our stroke volume. So the width of this box is the stroke volume. So as this box changes size, it'll be right in line with the changes to stroke volume. So let's get a new page here. So we've said cardiac output, Q, is equal to stroke volume times heart rate. We know stroke volume and systolic volume minus our end diastolic volume. Now, what are the determinants for our end diastolic volume? Which is also, this is our preload. End systolic volume is affected by two properties. Afterload and contractility. If you can't squeeze very much, can't get enough stroke volume out, so your end systolic volume is going to go up. If you spend too much time in afterload trying to generate pressure for that isovolumic contraction, not too much time in afterload, but afterload causes you to be in too much time in isovolumic contraction, you're going to have less volume of blood leaving the heart, therefore your end systolic volume is going to go up. So those two are the major determinants for those. So let's look at preload. Let's draw our pressure volume curves. We put our points in. So we said before that point B is our preload marker. So let's say we want to increase our preload. In order to do that, you got to increase end diastolic volume. So we have a new B, we call it B prime. So A is not changing, but this bar goes all the way, that segment goes all the way out there now. C does not change because we have not changed afterload. So there shouldn't be A prime there. Just C. This will then follow to our D line, or D segment for the Frank-Starling curve, and come back down. So now you can see how much the stroke volume increased. By increasing preload. So therefore, increase preload equals increase in stroke volume. It is a proportionate relationship. Conversely, if you decrease preload, you will decrease stroke volume as well. You can draw that out on your own. Let's talk about afterload now. Same thing, let's draw our boxes. And label them. A, B, C, D. So now we are altering only afterload. So we're going to increase our afterload. We're going to go up to C prime up here. So A doesn't change. B doesn't change. We haven't changed our preload. The filling is still the same. Doesn't matter. It's all coming in normal. Now we've increased our afterload. Blood pressure went up. We have to go all the way up and meet this line now. However, we have the Frank-Starling curve to deal with. And let me draw that back in here. When we have the Frank-Starling curve, we have to obey those rules. And this C can only go to where the curve is. And then it stops. Oops, what happened here? Here we go. So it comes down. Now, because we've increased afterload, we operate on this curve. Look at our stroke volume. Decreased. Just because we increased our afterload. So therefore, increase afterload equals a decrease in stroke volume. Because now the heart has to take this much more time to generate the pressure to overcome aortic pressure and open up that door. More time spent doing that, less time in ejection, and we have to obey the rules and we decrease our stroke volume. Now, contractility. Same thing. Oops. A, B, C, D. Our contractility curve obeys point D, so we're going to be altering point D. Just because of the way that I drew this, I'm going to say that we are going to decrease contractility. Patient had a heart attack, the heart muscle is damaged, the contractility curve is going to shift down and to the right. So let me draw the damaged contractility curve. So that's our new curve. So D is going to be here now. Come down here. A has to change because we're going to be on a new curve here. But if you decrease contractility, stroke volume goes down. So I'll write the inverse or the real way it's supposed to be. We just drew the decreased contractility, but if you increase contractility, increase stroke volume, we did it where we decreased contractility and that resulted in a decreased stroke volume. So it's proportionate, same as preload. Afterload is the only one that is opposite. So this kind of summarizes these different parameters. The last thing I'm going to add to this are the factors that affect each one. So what factors affect preload? Increased blood volume, skeletal muscle pump, deep inspiration, atrial systole, and the last one is venoconstriction. These are all things that are going to enhance preload. Let's move on to afterload. What affects afterload? Increased blood pressure. We'll call it vascular resistance. These are the factors that affect afterload. Frank-Starling is the main thing that contributes to the contractility. If you increase contractility, remember, as the heart stretches, it becomes more sensitive to calcium and a greater contraction. You want to increase your contraction, end diastolic volume will do it as well. The bigger the end diastolic volume, the bigger the stretch, the more forceful, more vigorous that contraction is going to be. Remember also, as the heart stretches, it becomes more sensitive to calcium, and you get a more forceful contraction. So those are the factors that affect stroke volume. With regards to heart rate is going to be your parasympathetic nervous system and your sympathetic nervous system are going to be the major determinants for your heart rate. So I hope that clears up things that was missed in class today. Let me know if you have any questions. Come see me. Thank you.